Thank you, Mr. Chairman. Thank you, the Committee of Computational, to invite me to give this lecture. I will talk about, in particular, one subject called self-consistent clustering analysis, called SCA. And the whole idea would be we want to compute multi-scale material system, predict the response based on a microstructure. And I will show example based on composites and also advanced and additive manufacturing systems. The work are done mostly by my students, and because this is interdisciplinary research, I have a lot of collaborators, which listed here. So I will give you some idea what it means, how mechanics and physics can apply to microstructure systems. You can see the evolution of composite material, how they evolve as a function of time. And you start from a traditional material, I would not call it too traditional, would be, say, fiber composite, all the way to nanocomposites. And also now, we really want to look at the nanoscale using additive or advanced manufacturing technology, which is this one is based on the work done by Caltech, and the diameter of this truss system is around like 10 nanometers, very, very small scale system. So the question would be, how can we accelerate structural and material system design accounting for process structure property relations? That's the goal of my talk. So I will start with talking about something called data-driven approach. And this is a theory that we borrow a lot from micromechanics called self-consistent. And the clustering is a lot more based on imaging technique, data compression techniques. We're going to combine both of them together and to demonstrate how we're going to look at microstructural response based on large deformations and so forth. Of course, it would be you create a lot of data. Okay. I know that data may be a buzzword, but I believe that there is a good application in mechanics or material science because we are focused on process. If you change a process, you get the microstructure, and the microstructure will change your properties. So that creates a lot of data. In fact, we talk about material, basically it's a database. So that's the reason why we talk about data, because you cannot just make it up. It depends how you process material based on thermodynamic, what composition. It has to be a material database so that you can use the information to predict the microstructure. Okay. So the objective would be, if you have such a complex data structure, how can we effectively and accurately predict the nonlinear history-dependent response of this heterogeneous complex microstructure? But because this is so small, uncertain quantification is very important because you cannot just do deterministic approach. You have to go to a statistical approach in this problem. So the way it works would be you have data, and you look at the data, and you train the data. So we're still learning a lot. We work with mathematicians on this one. We call this offline or training stage. And the second one is called online or predictive stage. And for micromechanics, in particular for mechanics of material science, we use this Lippmann-Schwinger equation and also micromechanic mean field theory. We borrow these two theories to do it. And the whole idea that we call this is self-consistent clustering analysis called SCA. So that's the one that I will focus on, and then we'll give a number of applications in this case. Now, what is the Lippmann-Schwinger equations? So basically, we look at the equilibrium equation, the constant equation, and in particular, I want to focus this equation is a deformation gradient. Okay? And the Lippmann-Schwinger equation, basically, we look at this equation, we rewrite this in a different form, okay, and you make some assumptions, okay, and then you do an iterative scheme and try to do the corrections. And this theory is started in, we learned it in 1950 from this paper. That's the reason I call it Lippmann-Schwinger equation. But then it converted into mechanics from a statistical mechanical point of view in 1972. Now, the second thing is called clustering. So the whole idea would be we want to cluster the data such that instead of looking on all individual material points, which we do it by either FFT or by Feynman calculations, I want to group the data in such a way that they have similar behavior, similar mechanical response, and there are different ways you can compute it. And based on this Lippmann-Schwinger equation, you describe this equation, and using micromechanics, you come up with the interaction tensor, and I will give credit to these two papers, which I learned a lot from it. Okay. So now we can put it together based on data, and I'm going to describe briefly what it means by training and also prediction. So for example, would be I want to solve this system, which is 300 by 300 by 20 in a three-dimensional structure. Look at how the response of this actual carbon fiber composite idealized. And if you just do it by finite elements, it takes about 80 minutes on a 24 CPU. And you use domain decomposition. There are a lot of clustering technique that we have not studied, but we just use one called k-mean clustering. And then you come with the interaction tensor, how this interact. Say, for example, will be based on this from that many degrees of freedom. I go down to 32 cluster. I can look at similar response within 1 second using one CPU. So the speed up is tremendous in this case. So that's the way we compress the data. Look at this data, look at similarity equation. Now, I want to go to do a prediction. And in the order of computation now, instead of n squared, because of this, it will be k cubed. Okay, so now the k is pretty small. For example, this is n, and this is k. So that's a big difference in computational time in this way. Let me give you some examples, in particular for software material. We borrowed the idea from FG square, finite element square technique. So basically it would be, this is a macroscopic response, and we discretize it with lots of Gauss points. Okay? And I'm going to loop on the step, and each Gauss point, I compute the microscale. But for solving problem, I need to break it down into three steps, and then I take a homogenization scale and feed it back to here. So that's one computation. But this one can be pretty large. Okay, for example, for this system here, I'm using 1200 by 1200 in the plane direction, times 10, 20, 30, and so forth in the other directions. So it's a huge amount of computational power, but we do this in the offline. We compress the data. Now I can do it much faster in this case. And loop on this on every single Gauss point. And that's the procedure that we do. So basically it would be, we assume a statistical distribution of the microstructure. And the key thing will be how can you actually loop over the whole system. Of course, if you know the location that's important, you can actually just take that part there. But just to demonstrate, we're going to loop in every single point. Let me give you an example. You can actually now, we don't need the constant equation, but we do need a constant equation of the individual phases and the mechanics and physics and chemistry interface. And now I can compute the constant equation on the fly before explicitly talk about the equivalent constant equation in this case here. Let me give you one more example in the three-dimensional calculations. I'm doing a simple problem with a crack propagation, 80 by 80 by 80. It has about 512,000 Gauss points. If you look at the computation case, I use this problem, this is a finite element calculation, with 154,000 elements, say 1-point integration. For each RVE, I'm talking about 512 Gauss point. And if you multiply that, that's a computational cost you need to do for direct numerical integrations, direct DNA calculation. I'm going to do data compression. I only use 10 clusters, and that is my computational cost. And based on this RVE calculation, if you compute everything like this, it takes about 10 to the 5 days to do the calculations. And I can do this in 56 hours on the 7-2 CPU. The speed up is about 43,000 in this case. And not only that would be, we can actually look at each Gauss point how the microstructure evolution is, because that is where we're interested in, where the initiation of damage, so that we can design a material to minimize the damage in this case. You can look at the low deflection curve at the same time, look at damage, look at stress distribution, and that's where now you can try to come up with design of the microstructure on the fly. Now, we're working on another project on unidirectional fiber composite. I want to model every single composite on this particular frame. This work is together with Ford Dow Chemical, and our goal here would be model the detailed microstructure of this system. The problem would be we don't have that much data, so we need to do an inverse problem to get a statistical distribution of the microstructure. And the whole idea would be we want to model every single detail. That's the whole goal here. And then you can come up with design experiment to calibrate your model, and then you can do prediction of different kind of combination of the microstructure. So this one is a 22-ply system with different angles. Our goal is to model the detail of the statistics of this microstructure. Let me give you an example of what it means by this. So we can do a lot of imaging, but this is a very expensive imaging, and this is something that we work on how to do this equivalent statistical description of one patch. But if I have enough patches of this microstructure, I can get the statistical distribution. Then it's pretty large, because for a particular RVE, we are talking about something like this order of magnitude in terms of microstructure. And the question would be, how are you going to do data compression so they can compute the response fast enough in this case? So we are doing a lot of experiments, and this is the first prediction on it, and just a test system. But we also look at a lot of different kind of experimental technique. The problem will be they cannot really see what's inside the microstructure, which, like in metal, you can see a lot more. So we still need to think about how to actually predict the internal delaminations and also the imaging for this. Okay? Let me go to the other topic that, again, based on microstructure, but we talk about fatigue. The total fatigue life is governed by this equation. And most of the micromechanics or mechanics can do is for for low cycle fatigue. And you can see how this one come about. Usually you assume a crack, and you see how it goes, but mostly it's like void growth and coalescence. It's a pretty well-known way to look at a problem. But we want to look for the incubation cycle. That means we're focusing on high cycle fatigue in this particular problem. But this one is a low cycle fatigue. You can see how the crack initiate. They're not a straight line. They actually based on the microstructure, how the microstructure interact. And that by itself is a different topic that we can talk about. How do you compute this efficiently, predict the crack propagation for this. But for high cycle fatigue, we can talk about 10 to the 15 to 10 to the 20 cycle. We talk about 15 years to 20 years. So you cannot just use this technique to solve this kind of problem. So you do a different way to look at a problem. And our application is a lot more on biomedical stents. And if you look at the detail, using wire specimen versus actual stent, because of the geometry and the microstructure, is not that easy to compute this particular system. Let me give you an example of what it means here. That's a typical stent. And it's a very complex geometry. We assume in the region, this is complete shape, stress concentration, multi-axial fatigue. When you go down into, you have a lot of defects. When you go down in further, you have something called stringer. This is based on manufacturing. So basically, you need to simulate all this process and look at this, how to look at the incubation period, how to predict fatigue in this case. So it's a very complex problem. And you really need to do with the realistic microstructure-based fatigue modeling. Now, we have looked at three kinds of modeling. One is basically a traditional one. You do the traditional casting, melting, and extrusion. And then you look at the microstructure, and from there you can predict it. And the second one is using physical vapor deposition. And the third one is on additive manufacturing. So let me just focus on additive manufacturing in this case. So we do a dislocation-based crystal plasticity. These are all based on plasticity. That's related to this topic here. And we are focusing on this incubation period. There's a theory on this, on it, how here. The question will be how can actually predict fatigue life in this case. So this is something that we have done. You can actually look at the microstructure on the system. And we apply this SCA method on it. And based on our calculation for this small cluster, we are talking about many degrees of freedom, and we can get a speed up of 10,000 in the computation in this case. So this is something that we work with Cimne on how to apply the NX CAM system to do hybrid manufacturing. So it's all computer generated. You can get a geometry pretty accurate. However, what is inside the material when you make? What are the microstructure? How can you control the microstructure? And from that, the process change of microstructure. And that's the reason my database is so important in this case. So you do experiment and do simulations and do online monitoring, feedback control to control the microstructure. Now, of course, this is a framework that we're working on. It's not easy. I didn't say we got it done. But for 2 parameters, we know how to control it. Once you have more parameters, it is not easy. So that's the reason why we create a lot of database on this particular system. But in terms of the classical manufacturing, these are well established. This is a CAM system. The question would be where do you monitor the system? How do you actually control the microstructure that you cannot see in this case? Okay. So the whole idea, like I said, will be you have a lot of process parameter. You want to do a closed loop control. You need to do online monitoring. And the way we do it would be we do feedback control, but at the same time, I need a lot of database. And the database based on a lot of thermodynamics because of cooling rate, heating rate, all these are experimental database that you need to look at. So we look at the temperature, time history. That's one very important parameter that we look at. And this is the framework that we're working on. Okay, so we have a lot of modules. So we basically do a lot more on the mechanics part. On this part here, there's a lot more material science on the grain growth, dendroid growth. And we've come up with process, structure, and the prediction. In this case here is on fatigue. So we are developing different modules, but the thing will be we do need to work with a lot of expertise. This is one form of what we are doing with a small company, Material by Design. There are a lot of different processes. We call this offline data, and we break out different tasks, and that is our online predictions in this case. So there's a lot more than that we can learn. We are learning quite a bit on this thing here, but computational mechanics plasticity is very important in this particular example. Now, I'll give you one example. How we do would be we put a powder in. This is a powder bed system. You put a laser or E-beam on it. You try a different direction, you can see the void formation in this case. So we can actually know how to control, minimize void formation, but there are different kinds of void formation that you need to understand how to do it. Simulation definitely can help you to minimize the void formation. But there, like I said, there are different kinds, depends on the powder. There are a lot of physics that we need to learn about. And the second thing would be now we get this particular system. Now we'll look at the grain growth. dendrite growth, different phases of the material, so you have different material science aspect that you need to look at on it. So this one is called the cellular automatic finite element method. It's called CAFE model. Okay, and then now you put it together. You basically will be look at the grain orientation, that's crystal plasticity, and you have the void formation, minimize it, and now you can actually look at using the reduced order model, which I talk about SCA, look at crystal plasticity, and you can see here will be when you actually test it out in lower different direction, you get different stress strain law in this case. But we computed on the fly, based on the experiment, based on the computation in this case. Now we also do experiments. Okay, I mean. This is just a fatigue theory that I don't have time to talk about. But let's talk about how to actually validate this using experiments. So we went to Argonne. This is pretty expensive. We use synchronized X-ray computed tomography or also the EBS beam. So this one basically is look at voids only. Okay. Then you can do some other technique to look at different precipitate, different phases. So there are a lot of experimental data that we need to create from different process in this case. And then we look at, using this technique, EBS beam, to look at the grain orientation. To do this is not trivial from 2 dimensions to 3 dimensions. Okay. So that you make a lot of assumptions on it. And from there, you can put it together, the grain structure and the voids, and you do a offline calculation. You can do elastic or the plastic analysis, data compression. You can do clustering, and then now you use the Lippmann-Schwinger equation to do online predictions. And now you predict the fatigue life, and you design your microstructure. So that is what we not just design microstructure. You can also design the different phases that can give you the fatigue life that you're interested in this case. Yeah. Now. There are a lot of process parameters. I'll just give you one aspect of it would be this is input power. Input power is not well defined. What does it mean by that? Okay, but this gives you some example of 2-parameter system, and you can see how complicated the system is if you really want to look at prediction of microstructure and do online monitoring in this case. And both grain structure and porosity affect the fatigue crack incubation. Sometimes people believe that lower porosity tend to, but does not necessarily result in higher fatigue life. Okay, so the key thing would be it depends on loading direction, but it's a very complex loading directions because the crystal plasticity, crystal orientations, and with void, there's only 2 parameters we are looking at, but those are 2 key parameters we are looking at. But now we talk about different phases where you can see the design of the system is not trivial in this case here. So that's, like I say, would be data mining is one way, but we don't know how to use it yet. Okay, but you need to do data learning, which we can learn a lot from experiment and from simulations. And not only that, would be we need to do it, compute it on the fly. So in this case, you have to use a reduced order model, but the reduced order model has to be mechanistics, based on physics, based on mechanics or material science. So that is the whole goal of this talk. And I'm going to give my conclusion because the chair said I have 5 minutes left. The first thing I talk about is data-driven reduced order modeling. We developed a theory called self-consistent clustering analysis based on classical micromechanics and the Lippmann-Schwinger equation, which we borrowed from quantum mechanics, converted into statistical mechanics, and we also look at one aspect of clustering, but there are a lot of ways we look at. We have not explored on that part there. Look at data compression. And we come up with something called the mechanistic self-consistent scheme for online prediction, just like the way we do in the real experiment. Hopefully we can do that. But this, you look at a lot of data, try to pick the right data to do the fast online prediction. I will show you some simple example on it. And I have not talked too much about what we might do softening. is a very complex numerical technique. For this, we come up with a method that we break down the RVE computation into 3 steps to bypass the solving numerical issue. So this is a numerical problem, not the mechanics system. And we apply this to additive manufacturing. In fact, it will be hybrid manufacturing. So we combine with CFD and a lot of other things I have not talked about to derive the process structure property relations. But this has to do a lot of the material science aspect, not just computation, because you actually, some of them are experimental database. You need to come with the experimental database on it. And we provided the self-consistent analysis model with crystal plasticity to look at the fatigue life prediction of as-built parts. Thank you.